Hi everyone, my name is Neha and this is the 15th lecture on Introduction to Automation. In this lecture, we are going to learn about permanent magnet motors and some control circuits. Permanent magnet motor, it is a type of electric motor that uses permanent magnets rather than windings on the field. This type of motor is used in Tesla Model 3. In that model, it is used in the rear wheel drive. And recently, the Tesla models, they have started using a combination of permanent magnet motor at the back and a traditional induction motor at the front wheel. And there are many other applications which includes permanent magnet. For example, money changing machine, ticket machine, barcode scanner at supermarket, environmental control systems, in lawn mowers it can be used, in kids toys it can be used, camera, cellular phones, etc. are the applications of the permanent magnet motor. In this permanent magnet motor, there are three types of magnets which are used. First is Alnico magnet. This type of magnet has high flux density, but it loses its magnetization under some conditions such as a strong armature field winding. So in that situation, the magnetization will be low. Second is the ferrite. Ferrite, it has low flux density, so they have to be very large, but they are not easily demagnetized. So that's the benefit of the ferrite. And the third, we have the rare earth magnet. This type of magnet is made up from samarium cobalt or neodymium cobalt, and they have combined desirable properties of high flux density and high resistance to demagnetization. Now let's see next the relationship between torque and speed. So this picture is the permanent magnet motor symbol, and in this it shows how the applied voltage is feeding only the armature, and in this one it does not have field winding because this is a permanent magnet motor, and in this one it should have the permanent magnets, whereas the field wound DC motor which we saw in our last lecture, that one used to contain a field winding, and that was a one type of arrangement, and this is the other type of arrangement in which it has the permanent magnet. And this PM motor, it can be easily reversed by reversing the polarity of the applied voltage. Now here on the right you see the permanent magnet motor torque speed curve, and you can see how linear this curve is when compared with the wound DC motor. So you can see this one, the point here is called your stall torque, which is your maximum torque, and you can see how this graph is so linear with respect to the speed, and this is the highest speed, and the highest speed the torque will be 0. And the current curve is also linear with the torque, so as the torque increases, current also increases. So these permanent magnet DC motors, they are mostly used as a small DC motors, and they provide continuous rotational speed, and the speed can be easily controlled. So if we see the applications, then this permanent magnet DC motor, they are used in small size in toys, models, robots, and other such electronics circuits. Now next we have circuit model of the permanent magnet motor. To understand all the factors that affects the motor's performance in a particular situation, it is important to examine the motor load mathematical model. And that model is simply an equation in which each term represents the electrical or mechanical condition. And the circuit which you see here, this model basically is driving the mechanical load. So this is your mechanical load, and the equivalent circuit of the motor is in series circuit consisting of a inductance, which is represented by La from the armature winding, and then we have a resistance Ra. It is to account for wire and commutator resistance, and a voltage source. This is our counter EMF. So I hope you remember what is counter EMF. It is the internally generated voltage which increases with motor speed, and the polarity of this counter EMF is opposite of the line voltage, and together they create the line voltage and the counter EMF together they create an effective armature voltage. Here the inductance you see LA, it will limit the armature current, how fast that armature current can change, but does not affect the steady state operation of the system. Now by using the Kirchhoff's equation, we can write this equation which you have seen in the previous lecture also. VLN is the line voltage is equals to RA into IA, armature resistance and armature current, and this is the counter EMF. So solving this, we will get the armature current. So here the value of motor current is very important, because it is the electrical parameter that most directly relates to the mechanical torque. And for PM motor, the relationship between the torque and the current is very simple, and it is expressed by this equation. T is equals to K dash IA, where K dash is the motor constant and IA is the armature current. And here you see the same speed torque curve, and you can see how linear it is. Now next is the torque equation of the permanent magnet motor. And it says the mechanical torque on a free running motor, that is a motor when it is not connected to an external load, then in that case mechanical torque is given by this equation. So actually the motor together with its load, it makes up a mechanical as well as the electrical system, and this equation actually indicates some of the mechanical factors that will affect the motor's performance, which include moment of inertia. And this moment of inertia, it basically opposes any change in the speed. And then we have this bearing friction. Bearing friction is a constant, and then we have this D, which is a drag. It is also called windage. It comes from the air resistance on moving parts, and this air drag, it increases with the speed. So this equation, it is the mechanical torque equation on a free running motor, and this delta S you see here, it is a change in the motor speed per unit time, and S is the motor speed. Now let's see next. So when the motor is connected to an external load, then it will certainly have its own moment of inertia, friction, and there is now an external load torque which is attached over here. So an additional moment of inertia, friction, load, and drag factor will be added to it. So that's why we got this equation for the torque. This is a complete mathematical equation, and these are for the motor, and these factors are for the load. Now next we have DC motor control circuits. So to drive the motor, an interface circuit is required to convert the low-level motor control signal from the controller into a signal strong enough to run the motor. And there are two ways to do that. The first is the analog drive, and the second is the pulse width modulation. In analog drive, linear power amplifier is used, and you can see driving signal is coming into the linear power amplifier, and then this amplifier amplifies the signal which is sent to the motor, and you can see how the signal has strengthened from here. So here the signal was like this, and now here signal is more linear. A better signal is applied to the motor. So this is one of the way you can control it. And then we have pulse width modulation. So in this type the power is supplied to the motor in the form of DC pulse of a fixed voltage. You can see these are the DC pulses. So width of the pulse is varied to control the motor speed, and here we are using a class C amplifier. So with the help of this class C amplifier, we get the more amplified pulses, and the magnitude of that will be higher. So here you can see the wider the pulse, higher the average DC voltage is going to be, which means more energy is available to the motor. So there are actually two advantages of using the pulse width modulation. The first advantage is that the power amplifier, which is this, which we are using, class C amplifier, it can be very effective. And the second is that digital to analog control is not needed in this type, because the amplifier is, you can see here, either it is on or it is off, and it can drive directly with the digital signal. Where in analog drive type, it requires a controller. If the signal which is coming here is digital, it needs to convert the digital signal into analog. So in this, digital to analog converter is required. Now next we have a motor control circuit using the analog drive. As we have seen in the previous slide that linear power amplifiers are used in the control circuit, and these amplifier, they are the interface between the controller and the motor. And a class A amplifier, it is used, and it can be of two different types. One is the common emitter, and second is the common collector. So this common emitter, it gives the current and the voltage gain, whereas this common collector, it gives the current gain. The operation of both the types of amplifier, it is same. So what will happen when the base voltage, this VB represents the base voltage, when this base voltage it increases, then what will happen? The transistor will be turned on, and when the transistor is turned on, then the collector current, which is represented by this IC, so this IC will start flowing, and this IC is 3200 times greater than the base current. So base current is going into this transistor. So this IC, which you see here, it will go through the motor and provide the driving current. So that's how it works. Now there are some problems with class A amplifier. It is not very efficient. So let's see that in this circuit. So in this circuit, you see a DC power is given from here, which is of 12 volts. And then we have motor and the transistor connected in this way. So in this, let's consider two cases. The first case is that when the transistor is fully on, which means switch is closed. This switch is closed and current is flowing here. Then in that case, entire 12 volts will be applied across this motor. Okay, so that's the first case. And in that case, the current flowing is our 2 ampere. Okay, so that's the first case. Now in the second case, what will happen when the transistor, this is half on. So what does that mean? It means that your transistor, it is acting like a resistor in a series switch, resistance placed in series. So if this transistor is half on, then your collector current, which is coming here, it is also will reduce. Let's say it is reduced by half. So previously the current was 2 ampere. Now the current is 1 ampere. So if the current is 1 ampere, because current has reduced by half, then what will be the power dissipated by this transistor? So the power dissipated by this transistor is going to be 6 watt. So this is the voltage. So if you apply into the power equation says P is equals to VI. So voltage is 6 volts, and then current is going to be 1 ampere. So that will produce 6 watt. So that 6 watt of power is actually wasted in the form of heat, and motor is only receiving 6 volts. So that's how this class A amplifier is very inefficient when it is used as a used in a driving control circuit. Now let's see other motor drivers. And in this, first we have LM12, which is a power operational amplifier, and you can see its circuit over here. It has these resistance connected in this way, and then control signal is given through this terminal, and then it is driving the motor. So this is our motor is connected. So this is a high power operational amplifier which can supply up to 13 ampere with a maximum voltage of 30 volts. And this type of driving circuit, it's come in a IC in a single package with a relatively high current output. And here you see these are the equations based on this op-amp, and I hope you are familiar with this equation and how the voltage gain has been obtained by putting all these resistance values. Now next we have a power Darlington transistor. This is another type. In this two common collector type of amplifiers are used. First is this one, and this is the second one, which makes it a Darlington pair, and they are connected in such a way that one transistor is driving the another transistor, and in this the voltage gain is 1, but the current gain is very high. So in this, a small signal amplifier can be used, and this can be your op-amp, which can provide any voltage gain required by the circuit. So that can be used here to compensate for the voltage gain. So this was your power Darlington transistor, and then let's see next. We have a power MOSFET. So the power MOSFET, it can be used as a driving circuit, and these are different names for it. And this power MOSFET, it is designed to operate in an enhancement mode, which means that the biasing voltage is going to be positive. In this case, you can see here this is the output curve for a typical MOSFET, and the input range of the VGS is typically in between 0 to 5 volts, but it can climb up to 12 ampere when the voltage VGS is 13 volts. And this third picture which you see here, it shows the motor driver circuit using a power MOSFET here, and this power MOSFET has been connected in series with the drain, which means the FET will provide both voltage and the current gain. And here you see the gate is connected to a special op-amp circuit, and this op-amp circuit is designed to interface the controller with the FET. So this was the power MOSFET used as a motor driver, and this is the end of the lecture. So thank you so much for watching.